Alright, so I just wanted to add a couple of videos because I felt like it was a little bit incomplete. A couple of things from the last video. I finished with the gradient and the divergence operators. And then the one thing that I wanted to add is that those all those definitions work, but I wanted to make a slightly bigger point, which is you can have functions that are of other vectors or other second order tensors. In the previous two, they were functions of the position x, but you could have functions that are, for example, a scalar function that is a function of a vector field or a vector v. It doesn't have to be a field, so it doesn't have to change in space. So, but a function of some vector v, a scalar function. You can have a scalar function of some vector, some tensor t. You could have vector valued functions. For example, a function u, which is a function of the vector v, or function u, which is a function of some tensor t. Right, so these are functions in the usual way, tensor valued functions, but just the arguments can be either scalars, vectors, or second order tensors, and the output of the function can also be a scalar, a vector, or a second order tensor. So for example here, some tensor that is a function of some vector v, some tensor that is a function of some tensor t. And so these are scalar valued, right, vector valued or tensor valued, and the argument is either vector argument or a tensor argument. And this should just remind you of the standard, you have a function, like you have a function of x, that hopefully you know how to think about that, or you could have a function of several x's, right? And then you could say, oh, instead of having a function of several x's, I can say this is a function of the x vector. And similarly, you could have a function of components of a tensor, etc. And you could say, oh, this is, maybe I should use t. So in this case, this would be, for example, this scalar valued function of now vectors and tensors, not just f of x. So f of x, that would be the scalar valued function, nothing to do there. So this is sort of thing related to what you know about functions. So we're not really doing anything special here. It's if you think exactly the same way as you had before of functions, the only thing that happens is, for example, that now we're making the argument be, for example, a scalar, or actually this was correct. Let me just leave this here. A scalar for the argument, a vector for the argument, or a tensor for the argument, and then for the output, which is what I have for the columns. In that case, you could think of, now instead of predicting just a single f, what if I have a collection of functions? For example, f1 of x, I guess I didn't put the scalar one. So f1 of x1, x2, and x3, f2 of x1, x2, and x3, and then f3 of x1, x2, and x3. So instead of having that, I could say, I could put all those f's into a vector if they form a vector, right? Because maybe these are components of a vector. These f1, f2, and f3 are some components of a vector, and then it's a function of the components of a vector, of another vector, right? So hopefully the notation may look a little bit different to what you have used in the past, but actually you should think of it as a collection of functions with a collection of arguments. That's, I would say, more natural. Not exactly the same. The one thing that I would say, it's not exactly the same because obviously the fact that I'm saying that this is a vector valued function of a vector means that components only make sense once I define the basis. So the derivatives work even in any basis. So that's not exactly the same. So these f1, f2, and f3 are just three numbers. In order to call it a vector, they should be the three numbers associated with a specific basis. So that's just a little caveat. But the reason why I wanted to say think related to what you know about functions is because I think that may be a more natural way to think about these different, scalar value functions of vectors, scalar value functions of tensors, and so on. I think it might be easier if you think about that in the context of what you know about functions. And then just remember that when we say that something is a function of a vector, we mean the function of this geometric object, and it's going to be a function of the components once we define a basis. And similarly for the value of the function, so if I say this is a vector valued function, again, I'm gonna get basically functions for the components, but that only makes sense if I have a basis associated with that. And you have to worry about the basis. Obviously this you will change if you change basis, but it's the same vector that you get out. But the components might change in different bases. So that's just the caveat. And the way that we are going to do it is we're going to start with something that is components, or well, the tensor notation. We're going to take a derivative in a specific basis, and then we're going to rewrite it in something that doesn't have a basis. All right. So I just want to do a couple of examples. So what do I mean by these, vector valued functions or tensor valued functions? Let's just do a couple of examples. So I want to do this one of the tensor valued function of a tensor. So for example, let's say that I'm gonna do, tensor valued function of a tensor, and I'm gonna use the letter, I don't know if I want to use the letter F. Here I use A of t. I don't like this A. A usually I use for a specific tensor, not for a function. So I'm gonna use this letter F for function, but it's a tensor value of a tensor A, and I'm gonna say this is just give me A. So this is a function that if I give it a tensor, a second order tensor A, it will spit back that same tensor. So perfectly well defined, right? Just again, a function that I give it a tensor as an argument, for example this tensor A, and what is the output is the tensor A, right? So I want to take the derivative, and if you think again, think usual way, that would be f of x equal x, right? So that would be the equivalent. So in this case, f of a equals a, and I want to take the derivative of f of a with respect to a. So what is this would just be the derivative of a with respect to a. So what is that derivative? And here's where we are going to do it in a particular basis. So we're gonna say, let me just say, So this derivative of a with respect to a is going to be a fourth order tensor with components. So this is fourth order tensor with components. Delta ij, delta kl. And you can see that this has four different indices, so that's why it's a fourth order tensor. So there's an ij, a k, and l. So there's four indices, two that come from the thing that you are taking the derivative from, and two from the what you're taking derivative against. I don't know what the word is. And so what is this derivative, the incomponents? And for that, what you need to think about is in terms of the components. So this is once the basis is clear. This I would have to take, for example, what is the derivative of dA11 with respect to dA11? That would be 1. You know, the same way that if in the usual way, the derivative of f of x with respect to x is just 1. So this one is 1. But now we have 81 combinations. So the next one would be dA12 with respect to A11. That one is 0. dA13 with respect to A11. That is also 0, and so on. dA12 with respect to, oh no, 12. Let's do 2, for example. With respect to A11, that's 0. dA22 with respect to 2 is obviously 1, and the other ones are 0, right? So this is basically bunch of zeros, and it's only 1 when the component that we're taking the derivative at is the same as what we're taking the derivative against, and so that means that I has to be equal to k and j has to be equal to l. So this actually means delta ik, as I said, this is 1 if I equals to k, 0 otherwise, and delta jl, that implies j has to be equal to l, because it's 1 when j equals to l, but 0 otherwise. So that's pretty much it. So for a function that basically just leaves a, derivative of that function, which is basically derivative of a with respect to a, is a fourth order tensor whose components are this in the basis. So given that we have chosen the basis and we know the components of a in that basis, then the derivative has these components. Actually, you can